Hey everybody, welcome back. We spent the last couple of videos exploring the effect of transforming variables by adding and multiplying stuff, and what that effect is on the mean and the variance, or the standard deviation. And I bet you that you kind of thought that was, maybe vaguely interesting, but probably really not that important. But what I want to show you for the next 5 minutes is that you've actually been using the effects of linear transformation probably throughout your entire stats course so far. Turns out that whenever you've been dealing with standardized variables, these z variables where you subtract off the mean and divide by the standard deviation, that's been a linear transformation. So standardizing and linear transformations, they really are the same thing. And so I'd like to show you, using these new tools you've just picked up in the last two videos, why standardization has the effect that it actually does. Let me show you. So if you've got some random variable x, and you transform it by, let's say, adding and multiplying by something, you get these new expectations and new variances. So let's say that you've got some random variable z, and it's equal to the original x variable, but then you multiplied it by something and added something. And these two formulas will tell you then what the expected value of z is and what the variance of z is. Now I chose z here purposefully. In previous videos I had used a y, but here I want to draw your attention to this fact that if you've got some random variable x, then the average of x is some number. And the variance of x is also some number. Let's call it sigma squared. Likewise, the standard deviation of x is the square root of that. It's just sigma. And I don't know what the expected value of x was. It could be some weird number, and the variance could be some weird number, any old number. But we've been arguing that if you standardize, in other words, if you take your x variable and you subtract off the mean and you divide by the standard deviation, this new variable that we're going to call z has got some really nice properties. The property that its average is 0 and that its standard deviation, as well as its variance, is equal to 1. And that kind of seemed magical, I think, for most students. Why is it that the simple transformation of subtracting the mean and dividing by the variance gives you a mean of 0, which is nice because that adding 0 doesn't change anything, and multiplying by 0 simplifies everything. And likewise, standard deviations of 1 are nice because multiplying by 1 is pretty benign. So why is it that if you have x but you standardize, you get a z? So I want to show you why now. What is the expected value of z? Now z is a plus bx, but in this case, I want to point out what exactly z is. In fact, let's start there. Z was x minus the mean, and then divide by the standard deviation. We can just as easily express that x over sigma minus x bar over sigma. Or to be like really pedantic about it, we could do 1 over sigma times x plus this negative thing, negative x bar over sigma. And if we write it in this way, I think it becomes a lot more clear that this acts as the a term right here, and 1 over sigma acts as our b term, where we took our original x variable, multiplied it by b, and then added a to it. So z is a linear transformation of x. It just maybe didn't look like a linear transformation in this original way, but if you just expand that fraction, It sure is a linear transformation. So let's see why this has its particular mean and standard deviation. The expected value of z, well, it's going to be a plus b, the original expectation, a was this negative x bar over sigma. B was 1 over sigma. And the expectation of x is just x bar. All right, so we got x bar over sigma minus x bar over sigma. That's 0. So there we go. Now we know why the standardized variable always has a mean of 0. Always has to. What about the standard deviation of z? So let's see if we can do that here in the space that we've got. It's going to be easier for us to work with taking the square roots of both sides. So we have the standard deviation of our transformed variable, a plus bx, is equal to b times the original standard deviation. So st dev of a plus bx is equal to b st dev x. Standard deviation of z is equal to, all right, so what is b here? B was 1 over sigma, and the standard deviation of x was sigma. Okay, so sigma over sigma, that's 1, which was the second thing that we wanted to prove. So there you go. I think that is a nice reason for learning these transformation rules, is it helps you understand what was going on when you were standardizing variables. Okay, thanks for listening. Check out the next video. We're going to keep talking about the effects of linear transformations and linear combinations now of random variables, like what happens when you add and subtract random variables. Thanks for listening. Bye.